this video, we are going to talk about double Fourier series. So, what is it? So, first of all, let's just recall that if you have a piecewise continuous function, so let's say f of x is given and it is given to be piecewise continuous, right? Piecewise continuous and 2 pi periodic. Then we have a Fourier series, representation of this function, right? Then the Fourier series is given by this. Fourier series is, so basically Fourier series of f of x is this, right? Is essentially a naught plus summation m equals to 1 to infinity an cosine nx plus bn sin nx. And I am not writing here. You really, I hope you remember what are ans and bns. So these are basically 1 by pi integral minus pi to, so basically it is 2 pi period, right? So minus pi to pi cosine mx f of x dx, right? So those things are there, but you already know this. We are not going to talk about it. So essentially this, and here I will just write it like ans and bns are Fourier coefficients, are the Fourier coefficients of f. Yeah, Fourier coefficients of f. Yeah, and what do we know for the sake of it? See, we know that these basically the series, yeah. So these are the points we know. The series converges in the mean. Okay, converges in the mean. So these we did not prove, but this, of course, this is a little out of the syllabus. Okay, and you don't need it. This is true. So essentially what I mean is, if you take the partial sums, yes, and so basically let's say Sn's are partial sums, so the difference between Sn and f, if you take the square and then integral, so that can be made less than epsilon for sufficiently large n. Okay, so that is what it means in convergence in mean to f of x. Okay, and sorry, not f of x, to f of x. Okay, and of course we also, these we talked about, but we did not prove it, that if f is differentiable, continuously differentiable C1, then the convergence is uniform. The convergence is uniform. Gence is uniform. Okay. So what I meant is this. See, for a smooth function, what do I mean by smooth? As I told you in this course, basic assumption is, whenever we say smooth function, we always mean it is at least continuously differentiable. At least continuously differentiable. Okay. You can think of it as C infinity also. That's not a problem. So in infinitely differentiable function, but at least once differentiable. At least once. Okay. It depends on the context. If you are talking about situations where we need twice continuously differentiable, we assume that the smooth functions are C2. Yeah, so that's just the way we are thinking of it. Okay, so that's the idea. Now the thing is this, let's just understand it. What do we mean by double Fourier series? See, in PD, what happens is we talk about this partial derivative, right? So in PD, if you think about it, we talk about two variable functions, right? Two variables, x and y, f of x, y. And for now, let's just assume that this is continuously differentiable. Continuously differentiable. Okay, right. So what does this means? It means that, see, this is a two variable function, right? So differentiable, whenever we say, we mean that the gradient of f exists. Okay, that's differentiability. Yeah, I mean, wherever, at what point we are talking about, let's say this is differentiable everywhere. That is what we are assuming. So the gradient exists everywhere. Okay, that's what we are saying. And so when you are saying continuously differentiable, it means the derivative function, that is the gradient in our case, we identify it with the gradient, that is continuous. I hope this is clear. Okay, so essentially what we mean, continuously differentiable means the gradient exists and it's going to be continuous. And what do I mean by this gradient continuous? It means that, see, f is a two variable function here, so the gradient is essentially fx and fy, right? So basically this says that both f of x and f of y exists. Okay, so both partial derivatives exist and is continuous. Okay, so that is what we mean by continuously differentiable in this context. Okay, so we are given this function and we are going to assume another thing. See, let's say that it is a periodic function. Okay, so a small definition, let me put it as a small definition. If from R2 to R2 to R is called 2 pi periodic, is called 2 pi periodic. Okay, see, this is just a definition. I mean, please don't think, read too much into it. This is just, we are, defining something like this. So essentially what we are saying is a function from R2 to R. When is it 2 pi periodic? If this happens, f of xy, at any point f of xy, if the functional value, if you fix a y, f should be periodic with respect to x, 2 pi periodic. Okay, so this should be true. And again, if we fix x, it should be 2 pi periodic with respect to y. So it is x, y plus 2 pi. I hope this is very, very clear. This is very easy. Yes. So essentially, let's just draw a small picture and understand what's happening. See, let's say this point is x and y, right? And so this is your x, that's your y, right? X axis, y axis. Okay. Now let's say this is x plus 2 pi. Yeah. And let's say this is y plus 2 pi. This is just, I'm assuming it, nothing special here. So this is x, y plus 2 pi, this point, and then that point is x plus 2 pi, and then you have y. Okay, so what I'm saying is this, the function is 2 pi periodic if given any point xy. So this should hold for all xy in whatever domain it is. So in our case, let's say it is in R2. So for any point in R2, it should be true. Okay. So, see, the thing is this, what I'm trying to say is this, the functional value at the point xy should be equals to the functional value at the point x plus 2 pi y. Again, it should also be equals to the functional value of f at the point x, y plus 2 pi. Is it okay? Right. So, as an example, it is very easy to construct an example of it. So, let's say if I'm taking a function, c, f of xy to be sine x and cosine y, let's say cosine y or cosine x sine y, doesn't matter. Okay, so both are periodic functions. One is a periodic function in x, one is a periodic function in y. You can easily check that the above is true. It is easy to check that is 2 pi periodic. Yeah. Why? Because you see, once you fix a y, this is basically looks like a constant, and then this is 2 pi periodic. And again, if you fix a x, then this is the only function which is talking about, which we are talking about, which is again 2 pi periodic. So basically, this is true. Okay. So this is the sort of function which we are talking about. This is 2 pi periodic function when we are talking in the context of several variables. Let me put another question. Find another 2 pi periodic function. Okay, of course, constants are always 2 pi periodic, that you don't have to do all that, but we are not definitely not really interested in those constants. Anyways, so I hope you have an idea of what 2 pi periodic functions now. Now, with that said, what we want to do is we want to find out, let's say, even a function like this. In PDE, what happens is we always talk about several variable functions, right? So we need to know if we can find out Fourier series. If such a function, let's say, if I give you such a function, can you find a Fourier series out of it? Okay, so what we can do is see, and this is very, very easy actually. So what we do is, first of all, so this is finding the Fourier series, Fourier series of f of xy. So again, I am doing this thing in two variables. You do realize everything, whatever I am doing, that holds for several variables also. So basically 3, 4, 5, you just increase one more variable here and the exact same thing holds. So 2 pi periodicity formula and everything else holds. Okay, right. So we are just looking for, now we are just doing it for double Fourier series. You can do it for triple, and you can do it for 4 times Fourier series. Okay, so all of that can be done. So what's the idea? Let's just understand the idea. You can get the rest of it. Okay, first of all, you fix a y. Okay, fix a y. So of course, y is in R. So once we fix a y in R, you see f of xy, it becomes a one-dimensional function, right? So you see f of xy is uniform. It's a one-dimensional function. You understand what I'm saying, right? See, it's a two-variable function, x and y. Once we fix y, then f is just a function of x. Yes, And of course, since f of xy, we are going to assume that, see, this is continuously differentiable, we are assuming, okay. So f of xy is 2 pi periodic and continuously 2 pi periodic and continuously differentiable, and C1, okay. So if we fix a y, so let's say that will be our phi y of x. We can define it like this, which is f of xy, okay. So this function is just a function of x, okay. This is how we write. This is the definition, okay. This means definition, okay. So now this function is again 2 pi periodic with respect to x, yeah. You can easily see that with if you look at the definition. And of course, again, it is c1 with respect to x, okay. So with respect to x, now for this sort of function, we know that the Fourier series exists. So what should look like? So phi y of x, let's say, which is by definition f of xy, and that Fourier series will look like this. Yes, a naught of see, you remember, right? Let's say that I'm given this function. Let's say f of x is given. Yeah, f of x is given. That will be written like a naught plus summation an cosine nx plus bn sine nx, right? See here, an's, bn's, a naught, these are constants, right? Now this is just a function of one variable. Now if I want to put it here, this a naught which I am writing, this should depend on y, you see, because this is for one fixed y. So if I'm running y, that a naught will change according to y. So a naught is a function of y in this case. So we'll write it like this. Yes, plus summation n equals to 1 to infinity. Now you see this an, again an, this will be again a function of y, not a function of x, remember, because we are talking about the Fourier series with respect to x. So an y cosine n x, yes, plus b n y. See here, please understand this thing. Cosine nx, sine nx, this is because of the expansion with respect to x, right? Now these constants generally, for any fixed y, this is just a constant. But the thing is, if y is varying, then f of xy has to be written like this. Yes, I hope you understand what's happening here. See, if you fix a y, let's say y equals to something, yes, I don't care, maybe 1. Yeah, so in that case, this function is basically a one variable function. It will look like this. And then this variable is basically a naught at the point 1, so basically some constant. And this is also constant, this is also constant. That's our original Fourier series, okay. So we are modifying it like this because that x and y part is there. I hope this is clear, okay. So one thing, let me just put it correctly, okay. Now you see, what about the coefficients? If you remember the coefficients, so where the coefficients where an of y, that coefficient is what? It is 1 by pi. See, it only depends on x, right, in this case. So basically minus pi to pi. This is for a fixed y, right? This is for a fixed y. I have fixed a y. So it is just on x, f of xy cosine nx dx, okay. And of course you have bn of y, which is 1 by pi minus pi to pi f of xy sine nx dx. Yes, okay. So with that being said, one second, guys. I hope this is clear. Everything is fine. Okay. Now, see these coefficients. If you look at, see this function f is continuously differentiable with respect to y also. It is continuously differentiable with respect to x and with respect to y. So this is continuously differentiable with respect to y. Cosine is also definitely continuously differentiable. Yes. So you see these coefficients an and bn, if you think about it, so these are c1 with respect to y. Note. Yeah. See, these are functions, right? These are functions. And as y changes, the value changes. So essentially what I'm trying to say is this: if you look at these functions, these are very, very nice functions, basically integral functions, and you can show that they are continuously differentiable with respect to what? With respect to y. So here this y is only changing. This is just a constant in this case, okay. You can think of it like this, okay. So with respect to x, and so what we can do is we can actually expand them. Yes, okay. So then what we can do, C1 function, with respect to y. So we can write it as this: an of y is amn, okay, plus summation. There are two variables, so you have to be a little careful of what you are writing. M equals to 1 to infinity amn cosine n my, yes, m y plus, so please keep in mind which is m, which is n. Yes, see here an is the function. Yeah, think of it like some phi of y. Okay, so n is fixed. It is with respect to the summation is with respect to n, so that is why this n is there, plus bmn and then sine my. Okay, so that's your Fourier series. What am I doing again? See, this is a new function, right? A-N-Y and B-N-Y, these are two new functions and they are continuously differentiable with respect to y. Of course, you do realize that they are going to be periodic also because of the definition, because f is going to be 2pi periodic, this is 2pi periodic, right? A-N-Y. So we can talk about Fourier series. So the Fourier series of A-N-Y is given like this. And similarly, the Fourier series of B-N-Y can also be written as I should write it as BMN, right? Let's just do it like, okay, nah, I should not write easy. Oh, that's the thing. We should be very careful here, yes. You see, this BMN and these BNs has nothing to do with each other, okay? They are totally different, okay? So, B and Y, the coefficients, we have to write it like this. C, okay, one second, I made a small mistake here. This should be 0, which one variable should be 0. See, an is fixed, yeah, m is 0, and then m equals to 1 to infinity. So m equals to 0, this is the term, and then the remaining term m equals to 1 to infinity is this. Okay, so b and y can be written as c n0 plus summation m equals to 1 to infinity. Yeah, again, when you do this double Fourier series, I am telling you, be very vigilant, because otherwise it may, because there are variables involved here. So it is C m in the Fourier coefficient I am writing in terms of C, Fourier coefficient of this function Bn. Okay, and then you have cosine my plus dmn. Okay, sine my. I hope this is clear. Okay, now where, let me put down what the coefficients are. Amn equals to 1 by c. Amn, this is 1 by pi was already there, right? And then you have another 1 by pi. So basically it becomes 1 by pi square. 1 by pi square minus pi to pi. Again, minus pi to pi f of xy cosine nx cosine my dx dy. I hope this is okay. Yeah. So these are these coefficients: amn, bmn, dmn, cmn. These are the coefficients which I am writing here. Okay. Okay. What about bmn? Bmn is 1 by pi square minus pi to pi minus pi to pi f of xy. Okay, one second, let us check. Bmn, right? So it will be 1 by pi minus pi to pi. Then you have another 1 by pi here, right? This is sine n y, right? Sine n y. Okay, so this is cosine nx sine ny dx dy. Okay, so the cosine part is already there. See, n y, this cosine part is already there. So I just have to figure out what this b is with respect to sine. So that sine part I'm just writing. Okay. So with the cosine thing, this is just the sine, and a is that first coefficient, this is cosine. So that is why it is cosine. Okay. So I should write this first and that later. But anyways, I mean cosine nx. Yeah, one second. This should be sine my. So this is what I'm saying. Yeah, there are two variables m and this thing, two things m and y, right? So you have to be very careful about it. See, think about it. What is bmn? If you think about this particular coefficient bmn, so this is the Fourier coefficient with respect to the sine thing. So it will be integral of that sine part will be there, right? So that's what I'm writing here. Okay. Similarly, what is CMN? CMN, we don't have to look at it. It is essentially the same sort of thing. Minus pi to pi, and then f of xy sine of nx cosine of my dx dy. Okay, and dmn is 1 by pi square minus pi to pi minus pi to pi f of xy. Okay, and then sine nx is already there. Yeah, and I just have to change this thing as sine my dx dy. Okay, so you see these coefficients a and y already has this thing, and then I have this bmn corresponding to that part is there. So I have to put everything together to get the original coefficients. So I hope this is clear now. Okay, so now if we substitute all this in our equation, yeah, what do we get? Which equation? This equation. Where is it? We wrote it somewhere, no? This equation. Huh? Let's say call it 1. So if we put everything together in 1, what do we get? Therefore, f of xy can be written as a 0 0, m equals to 0, n equals to 0 0 0, right? Plus summation m equals to 1 to infinity. Okay, a 0 m cosine my plus b 0 m sine my. Okay, plus again summation m equals to 1 to infinity. This is a n0 cosine nx plus one second, a and then c, right? C n0 sine nx. I hope I'm doing it correctly. It should be something like this. Yes, plus you have the double summation now. So this is m equals to 1 to infinity, n equals to 1 to infinity, and then you have this a n m cosine. So this should be a n m. I wrote it like this should be a n m. This also should be b n m, something like this. This should be d n m. This should be c m n. But I mean, it doesn't matter. You can write it like this. So it's not a. It's just a notation in this case. So it's not an issue. So let me write it this way: cosine nx cosine my plus b mn cosine nx sine my, right? Okay, plus c mn sine nx cosine my plus d. It's a little complicated, so please bear with me here. Sine of nx sine of my. Yeah, so this is the whole thing down. So this is called the double Fourier series. Double Fourier series of f of xy. Okay. So now let us look at some remarks. The first remark is this. See, if f is such that f of xy equals to f of minus xy. Okay, and f of x minus y is equals to f of xy. So first of all, what do I mean by this? See, what I'm saying is, let's just assume that if you have a f which satisfies these two conditions, if f satisfies those two conditions. Now, as an example, you can see, let's just construct something like this. Let's say f of xy is this. We need this, right? So it has to be symmetric with respect to, so f of x and f of minus x has to be same. So essentially, you see, if you are putting a cosine x, sine y, it's just an example, right? So you see, if you are putting f of minus x and y, you do realize that is going to be equals to f of xy. Is it okay? Now, again, if you want, let's say, but the thing is it, this example satisfies the first condition, f of xy equals to f of minus xy. Okay, now if I'm putting, one second, sorry, f of x minus y, let's see what happens. This is minus of cosine x and sine of y, which is definitely not equals to f of xy. Okay, so what do we have is, this example does not serve this purpose. Okay, both the purposes. So for us, let's say if we change this sine to cosine, so let's say this is cosine x, cosine y. Let's just understand this. Then you see that f of minus xy is definitely going to be f of xy. Yeah, and then again that will also give me f of minus x, x minus y, right? X minus y. This is true. You understand? So this is an example where both of these condition holds, and when both of these condition holds, the following is true. Yes. See, a of mn. Okay. In this case, the coefficient a of mn will look like this: 4 by pi square. Okay. Sorry. 1 by pi square. Sorry. One second. Let me just check. What is amn? Amn. Okay. Amn is 1 by pi square minus pi to pi f of xy cosine nx cosine mx dx dy, right? Okay. So in this case, we will have 4 by pi square. Okay. And then 0 to pi, 0 to pi. Yeah. This is because of symmetry, you know, of the integrals. You see, this here, what will happen is this, it is basically, this is a even function, this is an even function, the product is even function. So if you are doing an integral, it will become 2 times. So minus pi to pi, that becomes 2 times 0 to pi, right? That is why that 2 times this and 2 times 2 from here, 2 from here, that is why that 4 is there, right? So 4 times 0 to pi, 0 to pi. Okay, and then you have f of xy and cosine mx, cosine nx, and sorry, cosine n, one second, cosine, this should be nx, right? Cosine nx, sorry, yes, cosine nx, and then cosine my dx dy. Yeah, so this is this. So therefore amn is given by this, and f of xy, how can we write it? F of xy can be written as equals to summation n equals to 1 to infinity, summation m equals to 1 to infinity, and then a mn. See, I'm writing mn, it can be a nm also, doesn't matter, but basically something like this. Yes. Okay, and then you have cosine mx, cosine ny. Again, I did a mistake, sorry. So again, as I told you, you see, you have to be very careful here. Yeah, cosine nx, and what am I doing? Yes, this is fine. Yes, dx and dy. Is it okay? Okay, so that's your f of xy, and where f of x, a of mn is given by this. Yes. Okay, now the question is this: what happens to the other coefficients? Okay, so you can check. Please check this part. Yes, check that the other coefficients b of mn, okay, equals to c of mn equals to d of mn, which is equals to be 0 for all m and n, right? So see, I will not be doing all of it, but just let me give you an idea. See, essentially what happens is, if you look at b of mn, what is it? It is 1 by pi square, and then minus pi to pi, and then you have f of xy cosine nx, sine my dx dy, right? Dx dy. See, now if I want to take a change of variable, so basically f of xy equals to f of minus x, right? This two condition is there. So if you put it here, you see what is happening is this function, if you just taking, see, first of all, by Fourier you can do the multiplication first with respect to x and then with respect to y, right? So let's say with respect to x it becomes this. Let me do it here. So with respect to x it is 1 by pi square, yes, integral minus pi to pi. This integral is with respect to y, and then this is minus pi to pi f of xy. This is for a fixed y, okay, and then cosine nx dx, okay, and then sine my dy. I hope this is clear now. Okay, so this is by Fourier. We can do it by, because of Fourier. This is a continuous function, right? See, f is continuously differentiable. This is continuous. This is continuous. The whole thing is a continuous function. Fourier is true, and we can do this. Yes. Okay. And okay, 1 second. Yes. Let me. Yeah. Fine. Now you see, this is y is fixed. So this is just a function of x, right? So fixed y. This is fixed y. The part which is inside this bracket has a fixed y. So this is, sorry, fixed y. So this is just a function of x. As a function of x, f of xy is f of minus xy, right? So essentially, f is even with respect to x. Yeah. See, f is even with respect to x. Okay. And cosine, this function, cosine of nx, that is a even function again, even, okay, with respect to x again. Here the cosine is nx, so basically it is. So you see, the product of two even function is going to be an even function, okay. So you can just write it to be the 2 times 0 to pi and whatever that comes out. So f of xy cosine nx dx, so those part is there, okay. Now the thing is this, see, this part you have something, but the other part if you look at, so essentially it will be minus pi to pi, this sine my part is there, right? So from Fourier what happens is, if you multiply it from here, see, f again, I mean this is again equals to this, right? 1 by pi square minus pi to pi minus pi to pi f of xy and sine my dy and then cosine nx dx, okay. Yeah, again same thing happens. This is also by Fourier, this and the original integral are same. Now again, if you do the similar sort of thing, see, f here is with respect to y, it is an even function, but sine is an odd function. So the product is an even function of y, okay. So this product is odd function of y, for a fixed x, and between minus pi to pi what is going to happen? This is going to give me 0. So the integral of 1 by pi square minus pi to pi 0 dx is going to be 0, right? So in this case, see, this particular thing is a little complicated to, I mean, if you do it this way, then it is a little complicated thing to calculate. You better do it this way. So you first of all fix x and think of it as a function of y, and then you are done, okay. And similarly we can do it for the other parts also. I hope this is clear now. Yes, okay. So what happens is, b of mn is 0. You can similarly show c of mn and d of mn is also going to be 0, okay, right. So let's look at the another remark. Let's say if f of minus xy equals to f of xy, okay, and so basically it is even with respect to x variable, okay, but odd with respect to y. So even with respect to x, so you have a even function in x which is, let's say, cosine, and you have a odd function with respect to y, so basically a sine kind of thing, okay. So if something like this happens, then I again similar sort of analysis you can do, right? And you can show that the function you can actually reduce it. So f of xy can be written like this, can be written as 1 by pi square summation m equals to 1 to infinity, and then b of 0m sine my plus summation m equals to 1 to infinity summation n equals to 1 to infinity Bmn, right? So this is Bmn, and then you have cosine n, in this case nx sine of my. Okay, so this is the here b of mn. This condition, this particular part will be there. Okay, why 4 by pi square? Because even odd that integral is there, so there is two integrals, so 2 times 2, 4. Okay, so even integrals, if you are doing between minus pi and pi, there is a 2 times 0 to pi, that thing comes out, right? So that is why it is coming from here. So we can just calculate that part. It is integral f of xy, and then cosine nx sine of my dx dy. Okay, right. So now the thing is, there are other two cases. Let's say the other case, let's say if you have f of minus xy equals to f of minus f of xy and f of x minus y is f of xy. Okay, then what happens? So all I can say is, in this case, a mn, b mn and d mn are 0. Yes, so this is a I mean, you have to check this part, that what is the Fourier series in this case, what is the Fourier series. Okay, Fourier series. Again, one second, I forgot to write here. So in this case, you can check that a mn, c mn and d mn are going to be 0 for all mn. Okay, so in this case, this, and the last case, if f of minus xy equals to f of minus xy and f of x minus y equals to f of xy minus f of xy, then you can show amn equals to bmn equals to cmn equals to 0. Okay, so only thing which is remaining is dmn, and you have to do that. You check what is the Fourier series now. Check the Fourier series. Check the Fourier series. I hope this is clear. Exactly the same sort of thing which we did in the first case. Similar sort of analysis you have to do, and you have to figure it out. Okay, right. So before we close this video, what I am going to do is, maybe I will show you one example of how to work out. Okay, so worked out example, f of xy equals to xy, let's say f of xy equals to xy. Okay, so we want to find out the double Fourier series of this in the interval in minus pi times pi. Okay, and of course this is in this interval, and so we can just make it a 2 pi periodic function by extending it periodically. Okay, so that is there. Now you see, you have to check, since f of minus xy, if you are doing minus xy, this becomes minus x times y, right? And that is nothing but minus f of xy. Okay, and again, if you think about it, f of x minus y is nothing but minus x times y, which is minus f of xy. Okay, so in this case, what happens is, you see, this is the case of only the dmn remaining. So this last case, this is the last case. If you see, yeah, this is the last case. See, so in this case, only dmn remaining. And what is dmn? In our case, as I told you, you have to check it, but it is written like this: 4 by pi square, 0 to pi, and x times y, f of xy, which is x times y, sine of nx, okay, and then sine of my dx dy. Okay, this, if you check, you see, you use Fourier. Yeah, again, this is very, very important that you know how to work out Fourier's theorem. So you use Fourier and show that this is nothing but minus 1 power m plus n times 4 by mn. Okay, this part I want you to check yourself. This is a exercise. It is very, very important that you know how to do this thing. Use Fourier. There is nothing. So basically, take x with sine nx and y with sine my. You can do that because of Fourier, and take the integral separately. What and then calculate the whole thing down, you will end up with this. Okay, right? So therefore, what will be the double Fourier series? So the double Fourier series for f in minus pi and y between minus pi is f of xy, which is in our case xy, equals to 4 times summation n equals to 1 to infinity, summation m equals to 1 to infinity, okay, minus 1 times m plus n, and then sin mx sin ny by m. One second, this I did a mistake here. This is sin nx and sin my, okay, times mn. Clear? So this is what we are getting. Dmn is this. I am just putting it in the expression of f. You see, one second. So ABC everything is gone. You see, ABC everything is gone. I am only left out with this. So sin nx sin my, okay, and f of xy. So this is what we need to do. So you see, this is the term which you have. See, sin nx sin my by mn. Okay, so that's your f of xy, the double Fourier series. Clear? So although I will put it in an assignment, but for just an exercise, okay, just for an exercise sake, what I want you to do is try and find out the double Fourier series of xy equals to minus xy in minus pi. Do it and then see what happens. Minus pi times minus pi. Okay, there is a small mistake here. I should write minus pi. Okay, so this is the problem I want you to do as an exercise. Find the double Fourier series, and with this I am going to end this video. Thank you so much.